Hi everyone, welcome to Adams. Welcome to another round of tutorial. I would like to introduce you to the recurrent neural network. In today's tutorial, we've spent a lot of time on feed-forward neural networks and have already seen how they work in state-of-the-art deep learning libraries. And today we move on with recurrent neural networks. We look at some sequential data and try to revisit the concept of RNNs in Python. The tutorial, as always, is available for you on GitHub. Just have a look in our repository. And since we move on to this novel type of data, sequential data, the first part of the tutorial will deal with how we prepare sequential data for analysis. At least to some extent, we need to pre-process our data before we can put it into an RNN. And the minimal amount of pre-processing we just have to look at. So that is going to be part one. And then we look at recurrent cells, first of all, in their basic form. The idea is to code a recurrent cell, the functioning of a recurrent cell manually using Numpy. And thereafter, we do the same, but for a more relevant type of RNN, the long short-term memory, the LSTM. We will also try to implement its inner functioning using a little bit of NumPy code. And you might remember that in the end of the day, it's just matrix operations. So it shouldn't be too difficult, but it will involve a little bit of coding for sure. So ready yourself for that. And also the idea really is that we improve our understanding how RNNs work by trying to implement their workings. We will not go into backpropagation. We won't train our RNNs, so please don't expect any good forecast. We won't see any reasonable forecasts today. When it comes to training RNNs, the same concepts apply that we covered in feed-forward networks. Backpropagation through time is not fundamentally different from vanilla backpropagation. Rather, it's quite similar, but nonetheless, the math can get a little bit tedious, and we just won't go there. We train our RNNs in subsequent tutorials, obviously, but we do that using libraries like Keras. Okay, so that's it for the introduction. Let's get started. Going through my tutorial, obviously first we load libraries, configuring our environment. Have a look at that, there's nothing special. And I picked the task of forecasting stock prices as our use case. Remember what I said, no good forecasts to be expected today, so don't get too excited here. I'll pick the Amazon stock. You'll find the data on Moodle, but since the data is just a bunch of daily prices, this type of data is easily available anywhere on the web. And if you rather look at some different example, if you rather predict not stock prices, but some other time series, that's clearly possible, or you want to rather predict some other stock, that's easily done. You can change this data. It's very straightforward. Anyways, I'm using the Amazon data. Let me read that from my data file. And then let's have a quick look at our data. That's the standard format of a daily stock data. We have a date column. We have open, high, low, and close prices and the adjusted close price. And typically we also have information on the trading volume. Since our data is temporal data, a good approach would be to use the date column as our index in the data frame. That would allow us to use indexing, for example, to pull out all the prices of a given month. Saying, give me all the prices from the 1st of March to the 30th of March, 2020, for example. And we would not need to think, okay, what index, again, was the 1st of March, what index is the 2nd of March. We can just use the dates for indexing. That's clearly useful. So let's do that. Remember, we did something alike last time. There is a function setIndex, that we can use. And basically, we need to specify what column we want as our index. And because I want to change my data frame as opposed to creating a new variable, I can use the argument in place and set that to true. That should change my data frame in memory. And when I take a look at it again, then you see that now my index is the date column. All right, so far so good. I'm using head, could also use tail. Using tail, we see that I was putting that data by the end of March, so it's not super recent. If you want to update, that's easily done. Just download this data set from Yahoo Finance. Again, including the most recent prices. This data set stops at the 30th of March. And a little bit of more pre-processing here. I will consider the simple setting of predicting a univariate time series. That means that I want to predict the closing price. I won't look into high and low, nor will I look into the open price. I don't need any of that, nor do I need the volume. To keep things very simple, the adjusted close is everything that interests me. So let's get rid of all the rest. We are dropping some column here. Specifically, we get rid of open, we get rid of close because we have the adjusted close, we get rid of not high, but how, and also we get rid of low, and lastly, we get rid of volume. You could use indexing as well. In case you wonder, of course, you could use indexing, volume. That's it. These are the columns we drop. And since we're dropping columns, we are setting the index. And since, again, we want to do that in memory, we set in place equal to true. And here is our new data frame. Simpler. One more change. Let me, since I'm only having the adjusted close in my data frame, I don't really need to call that adjusted close anymore. Let me call the column price. That will keep our code a little bit cleaner. Oops, and now I did something wrong. Columns, that, did I misspell things? Oh, yeah, of course, silly me, because I changed the data frame. This line does no longer work because these columns have already been deleted. Let me reload it, and now everything should work fine. Yeah. Well, it teaches me that I should write my code in a more secure way so that it doesn't crash, but that would be an overkill for this tutorial. Introducing too many checks like, does this column exist? Is there an open column? Then drop it. Sorry for the mistake anyway. So now we have our data, and obviously we can plot that. Here's a little price plot over a time. I did not bother with labeling my x-axis using the dates. Could have done that. There is code available online. But since our series is quite large, we have 2,500 is here. Well, how many? We have close to 3,000 observations, and then putting all the date labels here on the axis would not look very good anyhow. So it's consecutively ordered from the earliest observation in 2009 to the most recent observation end of March 2020. And we see this rise, and of course we see certain impacts. That probably was the financial crisis. You all know what this impact here, the last one, is about. Remember, end of March. Anyways, that's our stock price. And if we now forecast that, the thing that this time series is obviously non-stationary, meaning that the values that we see, they do not fluctuate around a constant mean. If they do, we call this time series stationary, but they don't. There is a positive trend in the data, even when taking account of the coronavirus effect. still the overall trend in the data is positive. And in order to make the forecasting task simpler, it's common practice to differentiate the time series. Instead of forecasting the price development, including the trend, we get rid of the trend by taking the first difference of the time series. That means that we take the closing price of a day t, subtract from that the closing price of the day t minus 1, and that way we can get rid of the trend. And what remains in the data will just be the idiosyncrasy, that the change that of the change of prices that occur because of changes in the fundamental information, in investor perceptions, and all the other drivers, but not due to the overall trend in the data. So, all right, let's get the data stationary by shifting it. And once we've done that, I want to remind you that we will need to set up our data in such a way that we have target labels, or, well, labels. Today we are forecasting prices, so the target variable is continuous. Then we have our target variable and the inputs. And this picture reminds us, or take the equation, if you like that better. We will model the price in t as a function of previous realizations of our time series, previous prices, n previous prices. And graphically, we can depict that as shown here, that in the example, we take 4 price values, so 4 past days in our case, and use these 4 past days to predict the next day in the sequence. And then once we've done that, we roll our data forward in time and use the prices x2, x3, x4, and x5 in order to predict the value x6, the next point in the time series, which would be our second label. So x6 is equal to y2 in this example in the second time step. And we move on with that and roll our data forward in time to create a matrix that has this form here. We have observation in the rows, and our observations are a window of past prices. In this graph, we see 4 past prices, and the target variable is then the next price in the sequence. That data structure we need to create before being able to move on with recurrent neural networks. And this bit here, x1, x2, x3, x4, this window of past prices, that is going to be our sequence. In the example, we take 4 past prices, so our sequence length will be 4. Later on in the code, we consider a wider window, but just bear in mind, this is exactly what our sequence is, a set of past prices. And that is how you set up recurrent neural networks for time series forecasting. And we need to decide on the sequence length. RNNs are techniques to process sequential data. Sequence length is important. Okay, now let's first of all calculate the first difference in our time series. And fortunately, Numpy has a useful function that we can make use of. Data, it's price, right? Let me check. Yeah, it's price. So look at these prices. 3rd of March, 4th of March, 31st of March, date formats, 1st of April, 2nd of April, 3rd of April, and so forth. And there is a function called shift, and that allows me to shift my data by a certain number of periods. So let's shift the data by 1 period. Okay, so for the first observation, now I get a none. And then for the second one, I get values. I think it's better if we compare that. So let's have the original time series also on screen. And well, basically compare these numbers in the early bits of the time series. 73.42, that was the price on the end of March 2009. And after calling shift 1, exactly the same value, it shows up one row later. So I shift everything one row forward. That is to say, or the implication here is that now in this data frame after calling shift, I would see the stock price from the last day of March in the row that refers to the first day of April. So considering that this here is the first day of April, that's actually the last stock price, or the stock price one day before T minus 1. That's T minus 1. And because of that, data dot price minus data dot price shifted by 1 should take care of the differencing. So here's our differentiated series, all the differences between t and t minus 1. And since I cannot calculate t minus t minus 1 for the very first observation, because there is just no t minus 1, I get a none value here as my first entry. And well, that's certainly something we want to get rid of. Let's be a bit careful. I'll first of all begin with a temporary value and then say, well, let this here be temp, and then say temp equals to temp dot ilog. Well, ilog because I want to index using numbers, and then I can basically take all the values from the second observation, which is this one here. Remember, index 1 is the second observation, till the end for all columns. That's basically how I set up my data, or at least how I planned to set up my data. Here we go. So now I have, well, basically the point was to get rid of the none, and that gives me my new time series with which I can continue. So here we can right go, and you see, because I produced that error, and normally I do produce one error or the other when writing code live, that's exactly why we had the temporary value to not override our data until we know that our computations work out. Okay, just to double check. Okay, that looks okay. Oh, I had left the code to do the deletion of the none value in the notebook. We don't need it anymore, but you have it with some more explanation as usual on GitHub. Let's get rid of that, but let's plot our values. And before we can do so, we need to note that I have overwritten variable price. That should do the trick. But it doesn't. Well, let me, no problem. Let me just, conceptually all is well. Let me reload my data. Let me reload the data, and I will just Get rid of this bit. Don't need all that bit anymore. Let's calculate the difference. And once we've calculated the difference, here we go. And now we have our data again in an nice data frame. I was converting that implicitly into a series while I wanted a data frame. Sorry for the issues, but in terms of using the shift, all is as explained. That is now the structure of our time series, and that's also what we can plot. Let me plot that. Using just extracting the price values, putting that to plot will give us a plot of the difference, and then here is our data, but after taking out the trend. And what you clearly see is this increase in the variation. So the variations is not constant. We have this times of inflated variation, the crises that exist in the time period from 2009 till 2020. This will make our forecasting task a lot more difficult. Speaking about forecasting, we'll now split the data. And because we have temporal data, the splitting will not be done randomly into training and test, and rather we split it sequentially. That is the right way to do it, because if we were really trying to build a stock forecasting model, we would need to take the newest observations in the data as our test set, and then simulate the situations where we build our model on past stock prices and let it predict the price of tomorrow, day after tomorrow, and so forth. So what we can do is we first of all can compute the number of observations that we need to do the training, which basically depends on how I split my data. We could say we want to have 80% of the data in the training set, which equates to 2,214. And then we use that in, well, first of all, let's do the same for the test set, where then of course we use 20% of the data, and then let's use that to decide on our train and test set, or to extract them, which we can do using just vanilla indexing. We go from the beginning of our time series all the way to train size to have the training set. And considering the test set, we will basically go from train size to the end. And here you see that the way Python indexing works is quite convenient, that we don't have to add anything here at this point. By going to the largest index -1, so this observation here, which was this 2,200 something, it will not be part in the training set, but it will be part in the test set. So my code looks clean and nice. That's what I'm saying. And here is how we have partitioned our data. Next thing is to scale the data, where we, before putting it into a neural network, have to ensure a value range that will agree or will match with the activation functions in our neural network. So let's consider the training set first. We take the price in the training set. Since deep learning libraries typically want the data as a Numpy array, we can calculate that to Numpy. And when we calculate that to Numpy, well, let's have a look at the shape that we get. So that is basically the training set size, and the column dimension is 1. And then we can move on with the test set. And we can override these things. And now you see that if I write my code in this way, I have a problem because Numpy converts that to a 1D array. The conversion to Numpy makes a 1D array out of my training set, which suffices to store the data because I just have 2,214 values, stock price differences, and by default that ends up in a 1D array. But that would not match with the next step where my neural networks and also my scaling need a proper data matrix or my data in a two-dimensional form. So I cannot write my code in this way. And now I have to be a bit careful here. I need to recreate my training data and test data. And what you can do to correct for that issue, you need to reshape your data using the reshape function, which expects a tuple that specifies the dimensionality that you want. And one way of doing that is to let Numpy decide on the correct dimension on the first axis, but you specify explicitly that you want the dimension on the second axis to be equal to 1. Let me show you the effect, and then it will become clear. So that was the dimensionality of the trained data before using this reshape. And afterwards, I have that as a nice vector, which will be supported by the libraries that I'm using next. For example, the libraries to scale my data. We now scale our data, and this time I'm using the Midmark Scaler. And the reason I'm using that scaler is that it will basically map my data to the interval 0 to 1, which is a useful interval for neural networks. Previously, we had the standard data scaler that did the Z transformation. This one here does the Midmark scaling. And then we use the function that you have seen before. We use fit transform. But note that I use fit transform on the training data. This time we do it properly. Midmark scaling computes the min and the max over the bunch of numbers you put in. Price differences in our case. And these min and max value represent the parameters of our scaler. And by calling fit, these parameters will be stored in the object scaler. And thereafter, I can use these fitted parameters to handle my test set, where I just use the function transform. And that's the right way of doing it. So when transforming the test set, I will use the min and the maximum value that were computed from the training set. That's the proper way to do it, because the test set, in reality, it would not be available for you. Hence, you cannot, or you should not, transform your data, scale your data, before splitting it. Then you have some leakage in your data, and that the scaling and the parameters the scaling depend on will have seen all the data, including the test data. So that's the right usage of the scalers. Fit them on the training set, and then scale the test set using the fitted value. And you can imagine here, if you want to wrap that up in cross-validation and more complicated experimental designs, things can get a little nasty. But still, that is what we need to do. So let's run that. I'm not very lucky here today with my data. So the reshaping, supposedly I should first of all recreate the data. Probably there was one call too much. Here we go. Yeah, that's always the thing when you write code live. I would better split that up into different cells. Now I shouldn't rerun the code again because it's already scaled and already reshaped. So don't touch that anymore. But let me check. Can we plot that? Yes, we can. And that is now our price difference series for the training. And that's the one for the test. And if you think about it, that already looks quite alarming, and that the test data and the training data look rather different. I mean, resolution plays a role here. We have more than 2,000 observations in the training and only a bit more than 500 in the test. So resolution is an issue. But the training set, large parts of the training set have these periods with relatively little volatility. And the test set relatively shows much higher volatility. So just by looking at these two plots, you can notice that forecasting will not be very easy. But again, that's not our key concern today. No worries about the forecast. Rather, we will move on with our data. And this bit I didn't want to code live. I created this function here that will produce the matrix that we need to proceed. That function is to basically take a time series and a second argument, a window size, and using these two pieces of information, create me my data matrix where I have x1, x2, x3, x4. For instance, should my window size be 4, and then the next realization, x5, will end up in my target variable. And you see how this function returns me two Numpy arrays, one for x and one for y. And I'm calling that with a window size of 22. That is roughly 1 month. So we will consider the setting where we try to predict stock prices one day ahead by giving our RNN access to the prices in the previous month, or more specifically, the 22 past prices. That's what we do here. Let's run that. And here's our result. We have Y for the training set. I'm printing only the training set because you may have noticed that the number of observations has just decreased. That makes sense. You might want to debug the function a little bit. It makes sense because we use 22 past prices as our x. And the first point in our time series where we really have access to 22 past prices is the point x23. And all the previous values, there we can't really create our data. We have to wait for 22 days before we can start with creating our data matrix with covariates of xt minus 1 to xt minus 22. This is why we have lost a little bit of training data. That's common. Here's our window size for x, and that is going to be our sequence length. And then we have one more dimension. X is now a 3D tensor, which would be the way how Keras and TensorFlow like the data to be. Because we could process sequential data with more than one feature. We have only one feature right now, the price. But in order to predict the Amazon price, we could not only consider the past prices of Amazon, we could also consider, let's say, past values of the Nasdaq stock index or the Dow Jones index, or we could consider past prices of Google and other tech companies. We could have a multivariate setting. And this last dimension here is basically the number of, or is used as the number of features if you handle multiple features in one go. let's pull out some data. It's a Numpy array, so it's essentially a bunch of numbers. But in that bunch of numbers, we should be able to re-identify what we saw earlier, this matrix. Let me go up. We should be able to somehow identify this structure here, x1, 2, 3, 4, in our data matrix X, the one we just created. So it's hard with all these tiny numbers because everything is scaled to the interval 0 to 1, but let's give it a try. That is X. You see it's a 2D array. If I extract it like that, I get a 2D array. That is the first sample. That's the first observation. And that value here, at the end of our first observation, we should be able to find it at the second to last place in the next observation's covariate vector. So 26, 4, 5, 4, 4, and indeed 26, 4, 5, 4, 4. And well, actually, that also works out with other observations. So for example, the second to last one in the first observation, 0.27749, you find that as third to last observation in the covariate vector of the next sample right here. So although it's a bit hard to spot, you do have this structure in the data. And also, if you look at the training data, you should be able, that is supposed to be the target value for the first observation, and obviously it is not part of the first observation. But for the second observation, if we roll things forward, then this value, yt, let's call that yt, it should be part of the covariate vector when forecasting yt plus 1, because we move our window forward day by day, and indeed, 0.277944, 0.2779444. Exactly. So, and of course, if you pull out more data, it's not getting any easier to read, but now we will be able to also see the second entry in our target vector, yt plus 2, so to say. And we see how this has entered the covariate vector of the third sample. First sample, second sample, third sample, and here you have this 28 or 0.28 5407. So that is basically the point of this function here, create data set, doing the extracting the data to create these windows. All right, so almost set up. We could also basically re-append our target to the matrix X. I'm doing that here with this Numpy function, horizontal stacking. Then I get this shape once more, and that would also allow me to basically really have the data structure that equates to the figure we were seeing earlier. So after this H stack here, the last entry is the target, and that is xt, that is xt minus 1, xt minus 2, and then if you compare the observations, then yt is equal to xt minus 1 in the next round. And that value also reoccurs here. And now here you can really, if you look carefully, you can really see this pattern that is common for stock price, for time series modeling when we create our input data. Okay, let me reshape that before we move on. Xtrain. We use Numpy Reshape, and the function applies to our matrix Xtrain. Well, maybe before we do that, let's just remind us of shape of X train. Here we go. Okay, well, that's already in the right format. How about Y train? Is that okay too? Yeah, that's okay too. So actually, we don't really need to reshape our data. I just had that here, depending on how you play with the data in the previous step. In the demo notebook, there are some other steps that require you to go through that. But let me check. That actually is already quite right. So that is the data that we need. We need X as a 3D array, and Y we need as a two-dimensional data structure, as a proper vector, let's say. As a proper vector, not as a 1D array. We need that as a proper vector. And X we want to have in this format here. That is fine. And if you don't have that, you need to do some reshaping. That's, for instance, here the code. Let me just copy paste that to find in the tutorial. Numpy Reshape, training and test set, where we enter tuples of the number of observations. And the next bit is the number of covariates, which is equal to our window size. If you think about it, for a single covariate, the price, the window size is equal to the number of features in our data. But we will not look at it in this classical way, and rather we'll see where we have one feature, which is a price, and for that feature, we have a sequence length or a time window of 22 observations. And I know that sounds a bit confusing at the beginning, but this bit here is really important. When you work with RNNs, that is the data structure that you need to give them. Observations, dimension 1, axis or axis 0, axis 1 is the sequence length, which in our case is 22 because we picked it to be 22, and the number of features, which in our case is 1 because we only consider past prices of the Amazon stock. And that is exactly the point where would we also consider past prices of other tech companies, say Google, then that would contribute another feature. We would have 2 features. And for these 2 features, we would accordingly also have to provide all the past realizations. So we would also need this window of 22 past prices for Google. For every feature, you need the full sequence length. That is how you set up the RNN. And that gives us this data structure. And that allows us to move on with the recurrent neural network. Okay, let's first of all revisit RNNs. That picture is basically the structure of a feed-forward neural network, where we have inputs, hidden, and outputs. And you can think of a recurrent neural network as a feed-forward neural network that is basically unfolded in time, and the animation is supposed to illustrate that. We have a similar chain of input, hidden, output, just that the hidden state does not only depend on the input, it also depends on the previous hidden state from a previous computation. From putting a previous input in our time series or in our sequence into the neural network, and we keep the hidden state and let the hidden state also inform the computation of the hidden state in the second iteration. That is basically the interpretation of this nice little animation here. And we will try to re-implement that. Well, when you move on, you also see a picture which is somewhat more similar to the one I was using in the lecture. We pulled that from our blog, there is a post on LSTMs and RNNs, and it also makes this point that we have an input that's xt. We multiply that with some matrix, W, as in a neural network, as always in a neural network, but that alone does not give us the hidden state, because in addition, we have another multiplication of the result from inputting the previous input, xt minus 2, into our neural network. And the resulting hidden state also informs our computation of the hidden state corresponding to x2. And whenever we like, we can pull a forecast from the current hidden state where we need another matrix. It is here denoted as W out. So we have W in, the matrix that maps input data to the hidden state, W out, which maps the hidden state to forecasts, and we've got WH. That is a matrix that maps a previous hidden state to the next hidden state, or transfers the information from the hidden state. And by the way, don't be confused while we have a ReLU function here in this triangle, which is to denote the output layer. That is because in that blog post, the students were predicting crime occurrences, and the number of crimes committed in an aerial unit, like in a certain zip code, is a positive number between 0 and, well, plus infinity, essentially. And in order to model that, the group used a ReLU activation function in the output layer, which makes sense. It's exactly the same configuration that we were using in an earlier tutorial to simplify our manual backpropagation. But normally here, the output layer activation, as you know, depends on your task. It could be a softmax, could be a linear function, but as you see, can also be a ReLU. Anyways, let's try to look at the math again. We need to calculate the preprocessed input resulting from multiplying the input with the weights and adding a bias. With that preprocessed input, we can update our hidden state, taking account of the previous hidden state and adding a bias. And whenever we like, we can pull out a forecast from the current hidden state H2 using the weight matrix W out and adding a bias. And of course, all these weights need to be trained. We won't do the training. We will just randomly initialize them and look at the computations. That's the idea. Okay, some more explanations here, but let's rather try to write some code. My network configuration is such that we have 5 hidden units in the hidden layer. So hidden state will basically refer to 5 numbers. That's my hidden state. This vector of 5 numbers is to capture the patterns that I see in my input sequence, in my time series. It's exactly as last time. We need to decide on the size of the hidden layer. And I picked that size to be 5. How many features do I have? Well, one, it's just the Amazon price, past realizations of the Amazon price. That's my only sequence. Same in the output layer. I'm predicting the price 1 day ahead. So this is just a single value, scalar value. So the number of output nodes is 0. And we also introduce a little variable here for the batch size. I don't train my network, but if I were training my network, we would use batches. And also in the input path, we would essentially feed our neural network with batches of data. At least we could do that. So to be a little bit rigorous, let's consider a batch size parameter. Okay, now, and that's the interesting part. We need to set up these matrices. We need W in, we need WH, we also need W out. These are the same matrices that you have seen in the equations, mapping the input to the hidden to the hidden, and the hidden to the output layer. And also we need, corresponding biases. And each of these matrices and bias vectors we will initialize randomly. And well, to keep things very simple, I will be a bit ignorant and just use random numbers. I would not even bother with setting a seed. What really interests me is the dimensionality of these matrices. So input to hidden, that is where we need the number of input nodes, and my variable is input tim, and the number of state nodes, which is the size of my hidden layer. Let's copy paste that and see what we need to change for WH. We take the hidden state and map it to the next hidden state. HT minus 1 to HT. So here we need the dimensionality of the hidden state. And similarly, oops, that doesn't work. That doesn't work. That does work, right? Here we have the number of state nodes, but we need to map to the number of output nodes. So I really want you to make sure that this setup makes sense to you. But well, it's not that awfully complicated, so I guess it does make sense to you. And actually, there is an easier way to handle the biases. Let me copy paste the whole lot, then change every W for a B. And then, well, since we have biases that just go into the next layer, or the first dimensions can be set to a 1. And then the bias corresponding to the input layer, it flows into the hidden state. So we have the number of state nodes here. The bias for the hidden layer transition, same story. And the bias in the output layer, these signals go into the output node, so we need the number of output nodes here. That is it. That is the setup of our neural network. And we can take a look at this data now. So for the input, we have the number of input. Yeah, but that's just one, right? Because we have one feature. Number of input nodes is 1, so that should be 1 by 5. And indeed, it's 1 by 5. And WH should be 5 by 5. And indeed, it's 5 by 5. And by the way, since we have not initialized, same with the other matrices, we also need an initial hidden state for the first computational step, but we haven't seen any data, so we will just initialize the hidden state to 0. And here I was a bit lazy, so I just left the code. The hidden state, we have 5 units. Each of these units carries a value per, and that's important, per sample. We will simplify things and consider batches of size 1. So my hidden state is just a vector with 5 elements, but that is only because I'm considering sample size 1 or batch size 1, while I could consider larger batch sizes, and then I would store the hidden state for every sample. So I would need a vector of that size, really, which would then be a matrix. Sorry about that. Okay, we have all the parameters, weights and biases, and now we have an initial hidden state. So that should actually ready us to calculate the forward path. This little bit of code is to sketch how things would work in practice. When we calculate the forward path, we start with the first batch. So I'm pulling out a mini batch from my training data set. that training data set is xtrain. We pull out a batch using the very first observation, so starting the index from 0, all the way to our batch size, which is just 1, and taking all the rest. And the bit of code here is just to, well, printing out the dimensions so that we can keep track of that. Let me run that. But in fact, you see it here. Looking at that index, that guy here, that mini batch, should still be in 3D. That's the training data. I'm pulling out my mini batch, so it's just one sample, and that gives me this bit here. And when I want to do some algebra with my mini batch, it's more convenient to get rid of the third dimension, right? Otherwise, my code would look more complicated. So to illustrate what's going on with a single feature, I'm just using reshape once more and map my input data to into a vector with 22 elements, which is xt minus 1, xt minus xt, t minus 1, t minus 2, t minus 3, etc., etc., all the way back to my window size. So that is my x, basically. That is my sequence. That is my sequence. This is what I put into my RNN. That's my sequence. One feature, and sequence length is 22, so 22 values, the past 22 values for that single feature. That is my sequence, my input sequence, stored in mini batch. And you can try to wrap your head around. We can have larger mini batches, so the further dimensionality would grow, right? And we could have more than one feature, so the third dimension could grow. And that's really why we always work with 3D tensors when we really use Keras and other deep learning libraries. That's an RNNs, right? That's the type of data structure we have to wrap our heads around. Anyways, back to our simple RNN. We don't want to overcomplicate things. So the first input when we now process our mini batch. I mean, this is a little bit of an overkill because the mini batch just the batch size is 1, so there is just one example. What's the first input? Well, we have our mini batch of data, okay, and we go through all the samples. The batch could be larger than one sample. In our case, it isn't, but we go through all of them. And the important bit is this guy here. We take out the first realization, the first value in our sequence. We take out 1 x t minus window size, 1 past stock price. That is going to be our input. And personally, I found that a bit hard to understand when starting with RNNs, but it makes sense. That's how we process sequences, right? Let me go back to the animation. It runs a little bit fast and might be a bit hard to see, but you have better visuals in my slides. We take one input, calculate a hidden state. We then take the next input, update the hidden state. We then calculate a next hidden state for another input, and we do that really sequentially. Every single data point within our sequence is fed into the RNN, updates the hidden state, and triggers an update of the hidden state. And that really translates into this bit of code here. Where are we? Where we just extract a single value. But that is not going to work too well because I end up with, again, with these 1D array, but not a vector that I could use together with Numpy. And so what I will do is I pull out the first input in that way, 0 to 1, remember that the 1 indicates the last element, but remember also how the indexing works in NumPy. Long story short, that's just a way to save me this reshape. I could also have used the reshape, but this is the input structure that I want, because that will work with Numpy. So I need it as a 2D element here. Well, it's a bit hard to see why, but I think it will become clear in the next bit. So the first step was to process this input. So now we calculate this equation here, W in times xt plus B in. So the processed input is the dot product of our input value of our x and W in, our weight matrix, plus the bias B in. Okay, and there we are. That gives us an array with 5 elements. 5 is brilliant because that's what we need to integrate that with the hidden state, what we will do next. And this bit of code, which to me looks more intuitive, because we start with the first element in our mini batch, the first element in the sequence, in the second dimension of our mini batch. Remember, the second dimension, the second axis, is the window. That would be more intuitive, in my opinion, if I could write my code like that, but it has worked. But the reason why it has worked is due to this broadcasting mechanism. So this time Numpy has tried to solve things out implicitly, how to do the reshaping. And by looking at the numbers, that was successful. You see that the numbers don't change. That was successful, but that could equally be unsuccessful if I had set up my weight matrices the other way around, for example. Then the default behavior in broadcasting would not have worked. So to be on the safe side, I make sure that I get my data in such a way that the dot product can be calculated and that I know exactly what's going on here. Okay, then since we have the processed input, we can integrate that processed input with the hidden state using the previous hidden state. So let's say we introduce h state new is equal to, well, RNNs used to make a lot of use of the hyperbolic tangent. Let's stick to that. We need an activation function. I use the 10h function. And then we have the dot product of our hidden state and the hidden state transition weight matrix, WH. And we add to that the processed input. And we add to that a bias. And that should give us the new hidden state. Which, of course, has to be of dimensionality 1 by 5. So using that new hidden state, we can now, well, easily do the update where we basically just set the previous hidden state to the new one. Well, that is this equation here. And remember, we are still in the process of processing the very first element in our sequence. Done with that bit. We can basically take the next one, and this is how we would continue with sequential data processing. Now that we have updated our hidden state, we could pull out a forecast, but we won't pull out a forecast now. We'll do so later. We could now, having inputted the value xt minus 22 window size, we could get a forecast for xt minus 21, but that's not really the point of the exercise. Rather, we would input the next value in our sequence to continue updating the hidden state. So for the next mini batch, let's say second input, we go back to our mini batch, pull out a new value, always all the samples, and now we have, previously we had 0 to 1, now we had 1 to 2. And we should not misspell it, obviously. That's just a new pass price, this single value. And using this new passed price, we can do a little bit of copy pasting here. Process the input. So we take the second input, getting this intermediate result, the processed input, multiplying it with the weights, adding a bias, and then we could update the hidden state, which is the hyperbolic tangent of the dot product of the hidden state and WH. That is how we did it before, right? And to that we add our processed input. Or well, maybe we could also write that down in one equation, obviously, but now I have it calculated above. So let me run that bit. To that, we need to add our bias. And that should be it. That should be the calculation of the second time step. Just that we need to do the updating as before. And what's noteworthy here is that in the second step, unlike the first step, H state will not be initialized to 0 anymore. When calculating that, as we have seen above, H state now has a non-zero value. We were just looking at the shape. I did not run that bit. This is the current hidden state from inputting it the first price, the first element in our sequence, in our input sequence. That's the new hidden state. Now we take the second mini batch, we put that to our neural network, we update the hidden state, and get a new one. The previous entry here is just the processed input. The signal after putting this input price of t minus 21 into the neural network, mapping it onto the hidden state using the corresponding weight matrix. And that is our new hidden state. And we can continue like that multiple times. We'll do so shortly, but just one more bit. At any point in time, we can calculate a forecast by using our current hidden states. We just have done 2 updates. We have inputted the first 2 elements in our sequence, and we could calculate the output based on the current hidden state and the weight matrix that connects the hidden state to the output layer. Plus the bias. That's the output that we get. That would be the forecast that we get from xt minus 21. We started xt minus 22, and we did xt minus 21. That's the current step in our processing. Now we are pulling out a forecast, so that forecast is for the next point in the time series, xt minus 20 if you wish. And well, we can compare that. Let's look at the next point in our time series, which would be still a value in our mini batch. And since we had 0 to 1, 1 to 2, the next value would be 2 to 3. And you see how our forecast is way off. But that is not to be, that's not surprising. We are just working here with random weight matrices. We cannot expect this forecast to be any meaningful. We were to tune the weight matrix. We need to train the neural network. Maybe important here, the next step, again, it's this picture that's so important with the time series. When I sort of ask my RNN at the current point where we have done 2 updates, put in xt minus 22, we put in xt minus 21. If I now ask my neural network, hey, come on, give me a forecast, that forecast, by the way we set it up, is for the next sequence value, which is xt minus 20. So I need to look for xt minus 20, which I can find in my mini batch. What I could not do, and I think it's important to understand that. So this is wrong. I could not just look at y train. Normally, if I want to compare my forecast to the actual, I would look into y train, right? And well, that is a vector, but I can just call it and look for the very first element. Shouldn't that be the target value, this 0.2779? And the answer is no, because we set up our neural network such that we say, well, we give you 22 inputs. We have one input feature, x. We show you the past 22 values of x, and then you give me a forecast. And in y, we'll then find the value of the time series far ahead in time. So that really is xt plus 1. This value is xt plus 1. And that, if we interpret that output as a forecast, it is the forecast for xt minus 20. And hence we have to look into the mini batch. And what we will do next to wrap things up is we will write down our RNN as a loop where we do more updates, where we really go through one sequence in its entirety, and then pull out a forecast for the target y. That's easy enough. We start with reinitializing our hidden state to 0. That's, by the way, the default behavior also in Keras. More on that in a future tutorial. That's the default behavior. When we start with processing a new sequence, we initialize the hidden state to 0. We start from a fresh hidden state. We give it the values in our sequence, t minus 22, t minus 21, t minus 20, t minus 19, t minus 18, t minus, and so forth, right? And by firing these inputs onto our RNN, we hope that the hidden states accumulate to something that is valuable, that captures the underlying mechanics of our time theory, and from which we can eventually pull good forecasts. But when the next sequence comes, we start once more from zero. Default behavior. More on that in a future tutorial. But at least you've heard it once now. So we get our mini batch updater again, which is just the same bit as before. Let me run that bit. So we're pulling out this sequence for the single feature price of Amazon of 22 values, all the past realizations of the price. And now, for each element, each time step in this sequence, look at the for loop for t in range 0 to window size, so 0 to 22. Some print output doesn't really matter. We take the input, which we extract from the mini batch by indexing from t to t plus 1, as we did before. Again, making sure that we don't need to rely on broadcasting. Then we calculate the pre-processed input, or we calculate w times x plus b, as we did before, iteration in plus w in plus b. And we update our hinged state. This time we simplify the code a little bit, doing that in one row. We have the previous hidden state multiplied by its weights matrix. We add the processed input to it. We add a bias. And this is how we update the hidden state. And you see this recursion here, how the hidden state depends on whatever was stored previously in the hidden state. So we really have this accumulation of information in the hidden state. We see how our RNN now eats through the time series all the way to the end, 0 to 21. And now we have the full accumulated hidden state after seeing one sequence, one input sequence in its entirety. And from that hidden state, let's have a look. Well, it's just a bunch of 5 numbers because we have 5 hidden units. These values, we would hope to capture something that is meaningful for the time series. And as before, we can pull an output from that. Okay, which happens to be very close to 0. And that really is the output at xt, or after having seen the full input sequence. And we would hope that this forecast is any good. It's not as bad as the previous one, but this is only by chance. Without training, how would the neural network be able to know what these weights and biases should be? That's what we need backpropagation for, which we won't go into. But well, I just hope that this very, very manual, very rudimentary walk through an RNN helps you to understand it a bit better. And I honestly believe that we have seen some really important concepts here, how we iteratively eat through the sequence, accumulate, let the hidden state accumulate until the end of the sequence, then we pull out a forecast. That is the setup for this stock price forecasting example. Of course, there are other setups. We will look at other setups when doing language modeling in future tutorials, but that's it for now. And without any tuning, we revisit the working of the LSTM next, which is in a way just an RNN, but it's a more fancy RNN with this additional cell memory on top of the hidden state and all these gates to govern how updates of the hidden states are performed. You remember this picture from the textbook, Dive into Deep Learning? That shows us all the gates, the forget gate, the input gate, the output gate. That also shows us how we need a hidden state and an additional cell memory. And if we look really deeply into this picture, then we also see all the update equations that go on in these gates. Let's try to walk through this. Same as before, I'm considering a batch size of 1. I could use a larger, but I won't. And an input dimension of 1, so a single feature, just the Amazon price. I would also not change the window size, nor the output dimension 1, nor the number of state nodes. Everything remains as it is. Let's look at the gates. Here are the gates. Quite a bit of math, but it's not too bad. It's just mini neural networks, and we have coded neural networks before. Let's start with these. I mean, look at that. That's very similar to what we did before. We had just said x times weight plus previous hidden state times weight plus bias. And exactly the same for the forget and the output gate. Just that we use sigmoid, the sigmoid function here, in order to have really a gate, the values of which are either 0, letting nothing through, or 1, letting everything through, or something in between. And I wrote down the dimensionality of these matrices. For any matrix that involves the input data x, we need the dimensionality of the input d. And since each of these matrices maps x onto the hidden state, the second dimension of these matrices needs to be h, or 5 in my example, the one from the hidden state. And then we need a bunch of other matrices that concern the hidden state. And all these are have the dimension h by h. And then one more for y. To make the code a little bit simpler, I implemented a helper function as a lambda function, init x and h. This means that I'm just producing matrices of random numbers of this dimensionality. Input by number of hidden units, input units by number of hidden. That's this bit here. I have one function to give me as many matrices as I want of this type. And the other function is for these guys here, all of which are h by h. And with the help of these lambda functions, I can initialize all the 6 weight matrices that I need in one go. That's this bit here, right? And I call them in a hopefully telling manner, w underscore xi. That is x and input gate. That is x and forget gate. That is x and output gate. Hidden state and input, hidden state and forget, hidden state and output gate. There we go. Well, for the biases, we just have vectors and we initialize all of these to 0. Then we have the matrix that maps from the hidden state to the output layer, which is hidden state nodes by output nodes. And the bias is just the output nodes. And finally, we have the hidden state itself, which is just a vector with 5 elements, initialized to 0 as before. Right. What else? We have this candidate cell state and the cell state, the dimensionality of which is n by h, where n is the batch size. That's also similar as before. So I'm initializing that to 0. A candidate cell state I would initialize to 0 with the right dimension, batch size by number of hidden nodes. And then a bunch more parameters relating to the cell state, where we need wx, wh, connections to the cell state, and a bias. You see these here, right? When we calculate the candidate cell state, prior to doing any updates, we have the input multiplied by some weights plus the previous hidden state multiplied by some weights plus a bias. Hence, we also need weight matrices for this bit here. And that is what we initialize here. Quite a bit of parameters if you think about it. LSTMs, they exhibit quite a large number of parameters, so tuning these LSTMs is not a walk in the park for sure. Okay, so once we set up all these weight matrices, they're all just random numbers as before. But now we have set them up, we can look at the computations. Again, starting from a mini batch, we are pulling out a number of observations, as many as we want in our mini batch, and we reshape that to the format that we want to have, these 2D arrays we are basically creating here, that are 1 by 22 elements. That is my single input X, as before, my whole sequence, the mini batch. And this whole sequence, the mini batch is not the whole sequence. The mini batch could have multiple observations, it's a batch, but I always have all the observations in my sequence window per observation. So I have 1 by 22, and I'm now crunching iteratively through my sequence from the mini batch that has that entire sequence. I pull out the very first element and I call that X. And I call that capital X because in the equations above you've seen a capital X. Okay, so and that just is one number. So looks very much like a big matrix, but it isn't. It's just one number. And now, well, let's do these. Let's implement these equations. It's not so difficult. We have a sigmoid function. That's the sigma. And therein we see some dot product. So we need the dot product, right? And we have X by the corresponding weight matrix, which is WXI. That should work out. And then we have another dot product, which has the previous hidden state. So that's H multiplied by WHI. And then we have some bias, which is just the bias corresponding to the input gate. That should be it. Let's look at that. Okay. The input gate will be put together, integrated with the hidden state and cell state information, with the memory of the cell, and therefore it has to be of this shape, 1 by 5, because the batch size is 1, and the number of units we picked is 5. Okay. Well, it turns out that it should be quite convenient to copy-paste that, because when I now move on to the forget gate, well, that's just the same thing. But we have different weights. It's X by F, and it's H by F. And this would allow me to, and it's also a different bias, compute completely different values, but these values would need to be trained. Same for the output gate. You see how this is actually super easy. So the idea is also to demystify the LSTM a little bit, although, well, the magical part is maybe when it comes to doing the backpropagation, which we won't bother with. But knowing the forward path is interesting enough, I believe. So here is our output gate. Let's look at the next equation that we see in the LSTM, the cell state, where we start with a candidate cell state. Let's say C, this is C tilde. Okay, and apparently that is to be calculated as the hyperbolic tangent, so we need tan H. And then we have our input, but in a dot product, so np dot x by v, w, sorry, I keep confusing w and v. German, it's v. In English, obviously not. So that's w, and it's wxc, okay. And then we add to it another dot product, which is the hidden state, the current one. And there we have W hidden to cell state, HC. And obviously we see some biases here. So let's use the bias. that should provide us with a candidate hidden cell memory, which in turn allows us to update the cell memory according to the update equation, where we then see C equals F multiplied with C, the previous cell memory, which was initialized earlier on to 0, just in case. Now I'm ruining my notebook. That is 0. That is markdown. So this is an element-wise multiplication. That is exactly what the multiplication sign will give me. And to that, we add something in the input gate, element-wise multiplied with the candidate cell state, C tilde. There is my new cell state. And from that, we can finally produce our next hidden state, which happens to be the value of the output gate times the ton h of the cell state. There you are. That was the LSTM. All the way through these gates. And now we have our hidden state. How many updates have we done? Just one, right? We have the hidden state update after giving the LSTM the very first observation in our sequence window, xt minus 22. Nonetheless, we can try to pull out a prediction which would involve the dot product once again, where we take the hidden state and multiply that with the hidden state to the output layer and adding a bias. And that is our result. And again, we can compare that to the actual, the desired output, let's say. The desired output, which would be the next value in our time series, which would be x minus 21. And to find x minus 21, I need to look into, or I can look into my mini batch. I will not find that value anywhere in my output vector, y train. But in the sequence itself, find that, and it turns out that the desired output at this point would be 0.289 or 0.3, we could say. That is, again, of course, very poor forecasts, but as I said before, no good forecasts to be expected without training. The point is really how we use this thing. So in a nutshell, and I hope you agree, the LSTM with all these gates, that is no magic. It's just a bunch of more neural network type of calculations, a bunch of mini neural networks, feed-forward neural networks, that we introduce and put into our RNN cell. And remember, the point of these extensions is to overcome the vanishing gradient problem, that we avoid these very long chains of matrix multiplication when doing backpropagation through time. To fully appreciate that, you would look into the details of backpropagation through time for LSTMs. And at this point, I refer once again to this blog post, which goes through these steps in a great amount of detail. Have a look if you are interested. Otherwise, backpropagation through time, we'll use it next time and benefit from Keras, who makes that very easy, and we can just call fit, and that is all we need to do. One concluding remark, when it comes to LSTMs, there is the blog of Chris Oler, and it's a great post, and it's arguably the most popular resource when it comes to learning the LSTM. I highly encourage you to read that blog. It's great. Also, you find several other highly informative posts on his blog, but that one is very popular. And I want to raise your attention to the fact that Chris Ola uses a different notation, slightly different notation, which might confuse you. So if you, before reading Chris' blog, have maybe a look at this little remark here, where I'm basically showing how the notation that we use based on our textbook dive into deep learning and how the notation that Chris Oler is using in his blog are obviously the same. So what to take home, it's the same, but it looks a little bit different. So I put in some Numpy code that allows you to convince yourself before or after reading Chris' blog that our notations are the same. And other than that, this blog is very, very helpful. I just wanted to make sure that you don't get confused. Lastly, well, why did we actually use the hyperbolic tangent when LSTMs were introduced? And remember that Hochreiter-Schmidhuber did that a long time ago, 1998 if I'm not misled. The sigmoid activation was more common, and as the very last bit here, just reproducing a figure that we've seen earlier on. Using the tan-H in our neural network, we benefit from the fact that its derivative does not shrink gradients as aggressively as would the sigmoid. And you see that quite clearly here when plotting the tan-H and the sigmoid and their derivatives in one picture, how the derivative of the sigmoid really is super flat, and any values that we get, any gradients that we get when calculating the sigmoid derivative will be extremely small. And then multiplying these small values with more small values, gradient signals will just vanish very quickly. And while using tan-H alone is not enough, at least the gradients will not shrink as quickly because the derivative of the hyperbolic tangent just does not shrink input values so aggressively as does the sigmoid. Right, there we are. That was it. Well done. So we are already done with the RNN part, at least the manual part. And in the next tutorial, we can try to produce RNNs that are actually capable of doing some forecasting and train their weights a little bit. Thanks a lot for paying attention to this bit. I hope you enjoyed your manual walk through RNNs and LSTMs. And I look forward to see you in a future tutorial. Thank you very much. Take care and bye-bye.